Welcome to the Database Design and Normalization module. Of all the modules in this course, this one by far has the most amount of information packed into the small section of the book. Understanding the concepts behind a relational database and the importance of good database design will set you on the right track as a database developer. Access has a lot of cool bells and whistles you can incorporate into it, which we're going to look at in the coming modules. But unless a database has been designed properly, what good are all the fancy accessories? In this video, I'm going to demonstrate the process involved taking raw table data and developing a set of third normal form tables from that data. Before reviewing this material, please read Appendix A thoroughly. I'll make references to many of the terms the appendix covers, so it's important to understand those terms. When you're tasked with developing a database, what exactly is involved? Of course, you're going to be creating tables, queries, forms, reports, add functionality that automates processes. Doing all of those things will take time, but the majority of time when developing a database is spent gathering the requirements for it. What exactly does requirements entail? Obviously, because it's a database, we'll need to know what data needs to be stored within it. This will involve looking at reports, invoices, current data storage systems in place, such as spreadsheets, accounting books, and so forth. While data is important, it's also vital to understand how that data will be used. Every situation is different. An organization may need a database to keep track of inventory. The data in this case will be used to fill orders and to replenish on-hand inventory. Another database may be used to set appointments for clients. Along those lines, when gathering requirements, you need to understand how the business or organization works, specifically in terms of the database itself. For instance, a service business, such as a plumbing company, might need a database that can be used to set appointments, create daily work orders, and invoices for work performed. The appointments would be created first by a specific user in the morning. Someone else would set up and print out work orders for the service technicians, and after the work is performed, another person would create the invoices and send them out to the customers. This is what's referred to as workflow. It's just as important as understanding what data needs to be stored in the database. Gathering requirements for a database system should be the longest part of the process. If rushed through, things will be missed, and trying to incorporate those items after the fact will create more work and headache than if the proper time had been taken in the first place. Over the years, I've specialized in creating a variety of different database systems. One in particular that I really enjoy designing are payroll database systems. There are different methods to calculate payroll. The most common are the hourly pay systems. However, there are other types of payroll systems. For example, a physician's payroll system is typically percentage revenue based. So how would such a system look in table form? First, a table is needed to store physician information, your standard employee table. If there are multiple clinics that a physician could work at, we need a table to store clinic information. We'll call this a centers table. In requirements gathering, perhaps we find out some physicians earn 20% of the revenue they generate, others 18%. Perhaps some are straight salary. All physicians have a revision fee per case deducted. Revisions, by the way, are when a patient isn't happy with the results of the procedure. Another physician will fix the problem, and they're paid a straight fee. For each case a physician performs, a revision is deducted and placed in a pool. If a revision is performed for which they're responsible, that fee is deducted from their pool. Going back to requirements, some physicians are charged a higher revision fee than others. We find there are a lot of variation between physicians to allow for this. To fix this issue, we're going to create an employee type table. This way we can set those variations and create employee types that can be assigned to the individual physicians. Now that we have three primary tables, employees, centers, and employee types, we can use those tables to create a work record for physicians. We add a work table to the database structure that contains foreign keys to the employees, centers, and employee type tables. What this allows us to do now, for example, physician A works at two different clinics. At one clinic, he earns 18%. At the other, 20%. We can now assign him as a specific employee type for Clinic 1 and another type for Clinic 2. Recall from the readings in the appendix the many-to-many relationship. In this case, many physicians can work at many clinics, and many clinics can have many physicians. The work table is the join table between the two. With it, we've transformed the many-to-many relationship between the employees and centers table into two one-to-many relationships using the work table. The employee type table allows for even more flexibility in defining how the physician should be paid. Another table will be needed in the payroll database as a pay period table. We need this to keep track of the dates for a particular pay period. With the work table and pay period table in place, we can now add the pay table. Here, revenue and case information can be added along with adjustment information that's particular to a payroll record. Revision information can also be added to this table. If a physician performs a revision, it will be added to their pay record. Along those lines, revision fees that are deducted from a physician's payroll is then added to a revision pool table, along with deductions for revisions that are performed against them. Tables are meant to store the raw data. We don't need to store calculations in the tables. Calculations can then be performed in queries, which become the basis for the final payroll figures, such as gross pay, net pay, revision fees, and so forth. So how long did this database design take me to come up with? To gain a complete understanding of the system, this design took months to come up with. A good database design does not happen overnight. It will take patience and the willingness to study the system involved. For this assignment in this module, you'll be presented a data set in the form of an unnormalized table. All fields will show within the table. However, in the assignments, you may be asked to incorporate a few additional fields, so make sure you read the assignment directions carefully. In this table, we're presented with data that's collected regarding school faculty and the committees they serve on. Faculty are required to serve on one or more committees. Each committee can have many faculty members, and a faculty member can participate in many committees. What type of relationship exists between committees and faculty given this information? The language kind of spells it out, a many-to-many relationship. For now, this is information we'll use later in designing the final normalized tables. Some other background information includes faculty join committees and serves for a few years and can later rejoin the same committee. The first task involved in the assignment will be to bring this table into first normal form. If you recall from the readings, a table is in first normal form when there are no repeating groups. What is a repeating group? A repeating group is when there is more than one value in a field. In a database, a field can only contain a single value. Why? Because if there's more than one value, it's nearly impossible to query the value from the field. Looking at the table, there are several fields that contain repeating groups. Faculty, join, resign, office, and the hire date fields all contain multiple field values related to the three separate committees. Where the repeating groups occur, related information is on the same horizontal line. For example, John Smith joined the Scholarship Committee on January 2012 and served until December 10th, 2015. He rejoined the committee on January 9th, 2017. His office is CN 332 and he was hired on August 10th, 2009. Before converting the table to first normal form, another important task to complete is converting fields into their smallest logical part. Look for fields such as addresses that contain street, city, state, and zip information all together. And in this table's case, faculty. Faculty contains both first and last names. A name field should always be divided into first and last names, and the primary reason is for sorting. Records are typically sorted on last name, and if last name is contained in the way it shows here, sorting the field will be very difficult. We'll divide the faculty field into first and last name fields. Finally, to convert the table into first normal form, we'll create separate records for each of the repeating groups. This will remove the multiple field values that are currently showing. After removing the repeating groups, the table now appears as such. Each faculty member and their service to a particular committee is displayed as a single record in the table. Although there are no repeating groups, what relational database design flaw does the table suffer from? Redundant data. Other than the join and resign fields, all of the other fields have values that are repeated numerous times. When a table contains redundant data, the table is subject to update anomalies. So for example, if you try and update Bill Nye's office location, you'll need to update all of the values. If you don't, the database will contain inconsistent data. Multiple values for Bill's office, and who knows which one is correct. Going back to the two fields that don't contain duplicate data, join and resign, here's a tip. Those fields will wind up in secondary tables. Before moving on to the next step in the process of normalization, you should look for field groupings within the table. That is, what fields logically belong together. In this example, the committee name and created fields are logically connected. The faculty first, last, office, and hire date also belong together. Join and resign fields appear to belong together as well. What is the purpose of doing this? When you look for groupings of fields, you have to determine a candidate key for that grouping. Recall, a candidate key is a field that could possibly be used as the primary key for that grouping. When data is presented like this, oftentimes it's difficult to determine what can be used as a candidate primary key. For the committee grouping, committee name can certainly be used. The name should be unique. The problem here, though, is once a primary key has been created, it can't be changed. So if the committee name is misspelled, you can't go back in and correct it later. A candidate key should be minimal in size. For faculty, we could possibly use first and last as a composite key, but what if there are two John Smiths? Now the composite isn't unique. Rather than looking for candidate keys with this data set, we're going to create artificial keys for the two primary groupings of fields. We'll add a committee ID field and a faculty ID field to the table and provide each record a unique value for the committee or faculty it applies to. After adding the IDs to the data, our table now looks like this. The committee IDs, 1, 2, and 3, are connected to their respective committees: scholarship, graduation, and sustainability. The faculty IDs apply to their respective faculty. John is 1, Mary is 2, Bill is 3, and so forth. Now that we have keys for each grouping, committee ID and faculty ID combine together to form a composite key for each record in the table. For the next step in the normalization process, we need to determine whether each field in the table is functionally dependent on the entire composite key or only partially dependent on one of the composite keys. The trick here: does the field value change when the composite changes? If it does, the field is functionally dependent. Let's start with committee name. Our composite keys should read as 11, 11, 12, 13, 23, 24, 25, 32, 32, 34, and 33. Remember, the composite is a combination of both keys. Looking at scholarship, there are composite keys for it of 11, 11, 12, and 13. Did the field value change? No. Committee name stayed the same. So it is not functionally dependent on the composite. It's partially dependent on which key? Committee ID. Scholarship stays as committee ID 1 throughout. When we move to graduation, committee ID changes to 2. Faculty ID changes a few times for scholarship, so committee name is dependent on committee ID. Moving to the next field, created, it's the same as committee name. For 1/19/2002, the composite changes, so it too is partially dependent on the composite. Like committee name, it's dependent on committee ID. When the created value changes, the committee ID changes as well. Moving to the next field, faculty first, looking at John, at first glance, the composite of 11 for the first two records would suggest that the field is functionally dependent on the entire composite key. However, looking at Bill or Barbara, the record for those two, we see the composite is different for their records. For Bill, he has 3 different composite keys of 13, 23, and 33. Barbara has 24 and 34. Faculty first is partially dependent on the composite. What key is it functionally dependent on then? Well, faculty ID is the only key that changes based on the value in faculty first. So faculty ID is the determinant of faculty first. Faculty first is functionally dependent on faculty ID. Going down the grouping, faculty last, office, and hire date all appear to be dependent on faculty ID. Finally, looking at the join and resign fields, how do they relate to the composite key? Considering both fields together, their values change with each composite key. So join and resign are functionally dependent on the entire composite key. Our findings show that committee name and created are dependent on committee ID. Faculty first, last, office, and hire date are dependent on faculty ID. And join, resign are dependent on both committee ID and faculty ID. Recall from the instructions, committee and faculties have a many-to-many relationship. From our table data, we've determined the fields that belong to the committee table and the faculty table. In a many-to-many relationship, a join table is needed to properly represent a many-to-many relationship. Within that join table, we'll include the join and resign fields. Remember I mentioned join and resign were indicators that they belong in a secondary table, and the join is that secondary table. The appendix mentions using a composite key in a join table, such as in our example, committee ID and faculty ID. Looking at the data here, what's the problem with doing this? Well, 1, and 3, are repeated, so the composite key won't be unique. You can incorporate the join field into the composite. This will ensure the value is unique. However, now you're using 3 fields as a composite key. There's nothing wrong with doing this, but that's a lot of fields to use as a primary key and not typically done in real-world situations. Instead, for a join table, create an artificial key, the same way we did here for the committee and faculty groupings, and then include the foreign keys from the tables being joined, along with any other fields that belong in the join table itself. For this example, committee faculty ID could be used as the primary key. Committee ID and faculty IDs would be foreign keys in the table, and join and resign fields would be included within the table. The final set of tables in third normal form for this database looks like this. The committee table consists of committee ID, committee name, and created fields. The faculty table consists of faculty ID, faculty first, last, office, and hire date. And the committee faculty join table brings the whole thing together. It consists of its own primary key, committee faculty ID, foreign keys of committee ID and faculty ID, and the join and resign fields. With the join table in place, a faculty member can be shown as participating in more than one committee at one time. They can also be shown to resign a committee and later rejoin it. With the tables in third normal form, there's no data duplication. There's a single record for each committee and a single record for each faculty member. If Barbara Brown moves to another office, only one record needs to be updated. For this assignment, we created a set of third normal form tables from a single table of data. From here, we need to create an ER diagram that represents this set of tables. Basically, it's an easy task. An ER diagram shows the primary key, foreign key, and fields of a table along with relationship lines between tables indicating what type of relationship exists. Here's what the ER diagram for this assignment will look like. The table name is indicated at the top. Within the table diagram, the keys are separated from the rest of the table fields, with the type of key shown to the left of the key field name. The lines between the tables show the type of relationship between them. In a one-to-many relationship, the single line that touches the table indicates the one side of the relationship, while the bracketed side indicates the many side of the relationship. Here the committee table and faculty table are both the one side of the relationship with the committee faculty table. The committee and faculty table only contain one key field, their primary keys. The committee faculty table contains 3 key fields, its primary key along with the foreign keys to the committee and faculty tables. What's the best way to create an ER diagram? Personally, I prefer using Excel. It's already set up having cells within the spreadsheet. It's easy to format, place borders around the cells, and insert lines and brackets. You can also use Word by adding tables. However, this is a tougher approach as the formatting can get tricky. If you have a scanner and can draw and write legibly, you can create the diagram by hand and save it as a PDF. There are a number of different approaches to creating an ER diagram. Use the one that works best for you. This will wrap up this module video. As always, rewind the video to the sections you need further review of.